And I would like to continue further with our last presentation, but not the least one, from Mr. Piotr Kabaciński from Wartsila, Finland, to give us a presentation on the future fuels outlook. And Piotr, I hope you've got your crystal ball today to give us a prediction of the future. And what is the fuel of the future?
Good morning. Ships are transporting 90% of all cargo in the world. During that operation, they are generating 3% of all greenhouse gas emissions. Therefore, IMO introduced a set of targets reducing carbon emissions comparing to 2008 level. At least 40% reduction by 2030 and 70% reduction by 2050. This chain of bubbles on the left represents the possible actions that the ship owner can take to reduce the emissions. The higher we go, the more expensive it gets. Starting from the bottom, optimized voyage means, for example, lower vessel speed or optimum vessel routing. Second bubble considers the energy need. This means all kinds of optimizations just to save as much fuel as possible. Next bubble is about power distribution, which includes battery hybrid systems to increase the efficiency. These three first steps, everything that is under the yellow line, will be enough to comply with the IMO 2030 target. Then, in order to reach the 2050 limit, the last bubble is top important. It is about energy generation, which basically means switching to green fuels. Here we have all fuels listed. They are categorized into three groups: fossil, bio, and green. Fossil fuels will be disappearing sooner or later due to the environmental restrictions. Biofuels can be serving as a separate topic, and this presentation is about green fuels. When I was making the research on this material, I found that naming is quite confusing. Names and abbreviations listed here, they all mean the same. To make it simple, power fuels are produced from renewable energy. This diagram shows several possible pathways to different power fuels. It is clear that the key building block here is the green hydrogen, not as a fuel yet, but as a building block. And before any green hydrogen is produced, the very starting point is the renewable electricity. And in fact, we need a lot of it. Scaling up is the only way to minimize the cost, because today renewable electricity is about 3 to 5 times more expensive. If we already can produce green electricity, then we shall send it straight to the existing grid. It is a no-brainer. This is the most efficient way because no energy conversion means the least possible losses. Sometimes, however, it is not possible to get connected to the grid. Either it's too far away or there is a too big supply of the green energy comparing to the existing capacity. Here is one example. Glomfjord is the most windy area in Norway, and there is no capable grid existing there. In such case, the power fuels will be necessary. Pretty much the same is with shipping. Green electricity can be used for short distance ferries or inland waterways, but ocean-going vessels will be definitely needing power fuels. As it was mentioned already, hydrogen plays the essential role as an energy carrier. But this hydrogen must be produced from renewables. Today, however, hydrogen is extracted from fossil fuels in the pollution-heavy process. Green hydrogen does not exist today. This is how the green hydrogen is produced. Water electrolysis is known for many years. It is how the oxygen is produced on submarines. When electricity starts to flow between the electrodes, hydrogen is formed on the cathode, oxygen on the anode. This animation shows the alkaline water electrolysis process, but there are also some other methods shown on the right. Here I compiled some of the main challenges related to hydrogen together with the hopes. And let's focus on these hopes. Hydrogen is used as an energy carrier. It serves as a building block for synthetic fuels. And many countries already have the hydrogen strategy in place. Let's take the European Union, for example. Total electrolyzer capacity in 2019 was 250 megawatt. In 4 years, it is expected to grow by 12 times up to 3 giga, reaching 1000 giga by 2050. Let's talk about the power fuels now, and allow me to introduce the 4 candidates to the Fuel of the Future Award. We discussed about the hydrogen already, but this time we will consider it as fuel. Hydrogen has very high energy density. 1 kilogram of hydrogen has almost 3 times bigger energy content than the gasoline. The problem is that this 1 kilogram of hydrogen takes 11 cubic meter of volume. Therefore, we must either compress the hydrogen at 700 bars or liquefy it at minus 253. And quite frankly, today it is hard to imagine such conditions on board any vessel. Now, how to use that hydrogen for electricity production? This can be done inside the fuel cell unit. It is a reverted process to electrolysis. There are already few suppliers offering the fuel cells even to the marine market, but I will say no more about this technology. Why? Because I am Wartsila and my heart is beating in accordance to the 4-stroke cycle. Wartsila dual fuel technology is already capable of burning hydrogen as fuel. We mix up to 25% of hydrogen with natural gas, and we do have the ambition to create the pure hydrogen engine. Moreover, we already know how to handle the cryogenic LNG at minus 160. Therefore, it will be easy for us to adapt to liquid hydrogen when the time comes. The next candidate is ammonia, green ammonia. During my research, I found an important quote that ammonia was a detonator of population explosion. For over 100 years, ammonia has been the main feedstock to make fertilizers. Thanks to ammonia, we are capable of growing more crops, feeding more people. Ammonia is easier to store than hydrogen. We need only minus 33 degrees to make ammonia as liquid. But green ammonia does not exist today, same as there is no green hydrogen to make it from. To produce ammonia, we need nitrogen, and nitrogen is not a reactive compound. So in the Haber-Bosch process, we are forcing it to react with hydrogen. This requires high temperature, high pressure, and a catalyst. And apparently, there is no better way yet than Haber-Bosch process. And here again, the solution is the Wartsila dual fuel technology. We can either blend ammonia with natural gas before the engine, or we can mix ammonia with diesel inside the combustion chamber in a specific ratio. When needed, we can easily convert our standard LNG pack system to something like ammonia pack. Next off is green methanol. As you can see from the chemical notation, green methanol is not a zero carbon fuel. Methanol today is made from fossil fuels. It's mostly used for production of chemicals and plastic. Methanol is easier to store than ammonia because it is a liquid at ambient conditions. As for renewable methanol, there are 2 types: biomethanol from biomass and e-methanol from green hydrogen and CO2. To produce green methanol, we need carbon dioxide, CO2, which has to be captured first before it's added to hydrogen during the synthesis process. Since 2015, we already have the valid reference of methanol as fuel on Stiena Germanica vessel, which was converted at Remontowa ship repair in Gdańsk. This technology can be transferred to all our portfolio engines. The last candidate on my list is the synthetic methane, which is basically the same molecule as methane. For the ship owners, it means business as usual. Something to keep in mind is that burning the synthetic methane in the engine is still related to CO2 emissions, but the way the fuel is produced is carbon-free. Our dual fuel technology is already proven in burning natural gas. Using synthetic methane is the best gateway to carbon-free fuels, because today you just operate on natural gas. Tomorrow you will convert the system to carbon-free gas. Now we can start summarizing. In principle, there are 2 possible strategies. The first is you do nothing and just wait for synthetic fuels to come. Second strategy is for those who want to become carbon-free as soon as possible. In principle, it means switching to fuel which doesn't include carbon, like hydrogen and ammonia. At first, you can start blending carbon-free gas to natural gas. Then, when the technology is mature enough, you switch to pure ammonia or pure hydrogen. The word omnivore means that internal combustion engine basically can eat everything. In the transition to green fuels, the engine is not the limiting factor. Engine as such will stay almost the same. The only changes inside are about cylinder heads and piston crowns due to the different compression ratios. So if the engine is not a limiting factor, then what is the problem? One important aspect to consider is the bunkering of the new fuels. Comparing to the energy content by mass, which is shown here, hydrogen looks really impressive. But considering the volume that is required on board, it looks somehow different. And maybe these bubbles will show it better. Each bubble represents the same portion of energy. So for the same energy content, we need 4.5 times more space for liquid hydrogen than diesel, or 2.6 times more space for liquid hydrogen than LNG. And these ratios consider just the volume of the liquid. They do not consider any special tank design, insulation, pumping, cryogenic. The final word. Here is our recommendation about becoming future-proof. Go gas now, go gas today. According to the research recently published by Sfera, using LNG as fuel is reducing CO2 emissions by 23% overall. And as it was mentioned already, by installing the dual fuel engines today, you are already making the first step towards carbon-free gases. So you will be able to use them whenever they come. Thank you for the attention.
Piotr, thank you for your presentation. It was an excellent summary of our webinar today. I mean, you had it all. You touched all the probable fuels, the next fuels, and of course, underlined the utilization of LNG, bio-LNG as well. It's still to be seen for a while.